Welcome you all to the Spark Research YouTube channel. This is Dr. Virchanda, Department of ECE, Assistant Professor. Here we are going to talk about the course VLSI Design and Technology. In this session, we will consider some previous year examples that has been already asked. So here you can see this question is already has been asked in the previous year, that is 2024. Here is the pattern. So patterns will tell you, so there will be the the questions from each unit, that is from unit the unit 2 and unit 1, like and then this is the from unit 3rd and unit 4th, and like that. So their total there will be how many questions? 8 questions, and each questions will contain the odd objective. So you have to solve either one 2A or 2B or some and similarly. So total you have to solve the 8 questions, right? So we are going to take some important questions which has already been asked in previous years, right? So first, the question 1 we are going to consider, which is related to your derive an expression to demonstrate the drain current of the MOS transistor in different operating regions. So actually how to find out the ID current, that is drain current in MOSFET. Similarly, this is also the give the condition for VGS, VGD and VDS for N channels. Again there is a question which is related to the derive the threshold voltage for this MOS. So this is very common question. So that is why I am going to consider this derivation of drain current, right? Okay, so here is the summary first. Summary means these are the very important results. So even if we did not remember the derivation for all these steps, at least draw this graph, the image, drain, terminal, gate terminal, and the gate, drain and source, and this is source drain, and this is a gate terminal, and this is body. So the current, that is ID, that is drain current, how much will it flow in this region, right? So how much will it be? So this is for linear region and here is for saturation region. So for saturation region, ID is equal to, you can write K into VGS minus VTH whole square, where K will be mu cox W by twice of L. If you can remember, you can also write this one, linear region is equal to ID is equal to mu cox W by L. This is can also be called as a K into VGS minus VTH into VDS minus VDS whole square by 2. And for your the this is for only ideal case scenario, but in actual the actually if you are going to calculate the drain current, then you can include the channel length modulation. Here you can see channel length, actually the channel length will also be affected due to voltage that you are applying. So whatever the channel length you are considering, that may not be exactly same. So if you are considering the channel length modulation, in that current, in this case the current ID will be slightly changed. So how much will it be changed? So it will depends on the channel length modulation. So here you can write ID is equal to ID dash into 1 plus lambda VDS, right? So as much you will increase the VDS, definitely channel length modulation current will change. So this is the real case scenario. So now let's talk about the derivation, how to derive these saturation current linear, right? So first, what is the target? Target is to, like, in order to calculate the I, that is current, current density. This is the much more important equation, right? What is that? J is equal to Q mu N E, and this is for diffusion. This is for drift and diffusion. Diffusion you may neglect, right? Because this is very less, mostly in the the nano ampere. So you may neglect. This is the important one, right? So let's focus on this equation. J is equal to Q mu N E. So mu is constant, that is the the mobility, N is the electronic charges, E in that is electric field, and Q. So two parameters are important, that is Q and E. So first let's find how much charge will accumulate in the channel length region. So our objective is to find the Q. So how we'll find out the Q? As you know the formula, Q is equal to V into C. So if we know the voltage that we are applying and see the capacitance, it will be easy to find the Q. So first find out the V. So VGS, you can how much VGS you are applying across this capacitor. You can find out VGS will be written like that. 8 VC plus minus VC, so that we can get the value of VGC along the capacitor. And VGC you can also consider at a Vx, and VGC finally here you can write the VGS minus V of x. So this will be VGC. So our objective is to find the voltage across the gate to capacitor terminal. So in this panel you can write, and using this VGC, now you can first find out the charge. That is actually now another objective is to find out the Q is equal to V into C. Now, so already we got the V and now C. C you can write COX. So now multiply, so B into C. So actually there is another VTH. VTH is the threshold voltage which is required to make the inversion layer, because before inversion layer you know the calculation of electric field is totally unnecessary. It will not be used. So only because your current will flow in the inversion layer, right? So then after finding the Q, just put all the values, and E electric field you can calculate dV by dx, right? dV by dx. So this is the final value of your J, and now just integrate. See, since this is dV by dx, so integrate and you will get the current, right? So here integration 0 to L and 0 to V. So integrate, you will get this value. So here is JL is equal to mu cox divided by L, VGS minus VTS, VDS, VS squared ds. So this is for your linear region, and put this value, that is VDS is equal to VGS minus VTH, you will get for saturation region. So finally your final current, that is ID is equal to Jn, that is the I divided by W. So you can write, so ID is equal to mu cox W by L, and then VGS minus VTH all square, right? So that will be final value. Okay, so let's talk one questions related to this. In this question, your resistance is given, VDD is given, mu cox, this constant is given, and VT is given. So you have to find out at which voltage your transistor will switch from saturation to linear. Saturation to linear means what? Saturations to linear means actually saturation is where the entire channel length is formed. Linear means just start to communicate the electrons, that just started to propagate the propagation of the electrons from source to drain. So how much? So VDS is already given, that is VGS minus VT. This is the threshold voltage. So actually our objective is to find out the how much voltage is required here. So according to the KVL, you can write VD minus VR divided by R is equal to your the current. This much will be current. So V by R you can just. So our objective is to find this V out only. So for the time being, you can consider X is equal to V in minus V out, and remaining things let's calculate. So this will be the equation, that is VDD minus X. Here just I am replacing and divided by R, and these values you can write like half of kx square. K is there again, the constant value, x is nothing, so we have considered this v in only, and threshold definitely we have to consider. So put the values and get the value of r. So all already we have the values of r. Put the remaining values and you will get the v in this one value, that is the 1 point this is 1.73. So this is the exactly way. Okay, so let's talk the one more important question. So from unit third, we'll see the normally the one questions is very common one, that is the implement the Boolean function, like any functions a b c plus d something like CMOS logic is right. Similarly, the this is another functions using the static CMOS and then PMOS, like some different again the expressions. So these are the very common questions, right? So we'll see that is how to design any function with a static logic function. So this is for your inverter circuit. Here you can design using the PMOS and NMOS. So output will be the A bar if input is A. So this is called inverter circuit. Similarly for AND gate. AND gate, like two PMOS, that is in parallel, and two NMOS are in series. So The idea to implement it simply, if you are going to implement for y is equal to a and b, so ab means nmos will be in series, pmos parallel, right? Here, since this is a into b, suppose this is a plus b, then pmos in parallel and nmos will be in series, right? So idea is that a into, just first draw for pmos or either nmos for anyone. So PMOS, like suppose PMOS in parallel, then NMOS will be in series. Same things. Again, if this is in series, then this will be in parallel. So same thing only. Okay. So how will you know that which one should be parallel or which one should be in series? So that you can find out guess from the the objective. Like suppose here A into B. So A into B, like first PMOS should be in parallel, like suppose abc, then a b and one another c, and here a b and another c, right? So this is the technique. Similarly, this is one more examples, y is equal to ab plus cd. So ab, and since this is plus in between, then this is in ab in parallel and then series along with the c and d parallel, c and d pi, because both are in multiplication, so both are in parallel. Just make it reverse, like here parallel, then here series, here again these are in parallel, so here these are in series. Likewise, you can see the another examples. So very simple idea. Just if you'll see carefully, you can grab these books, right? Pseudo NMOS, like very simple things. Just the remove the upper parts. That is no need to use the pull up. Just replace by one PMOS. So okay, so one questions we are going to consider from the another unit. So here mostly questions are, the coming related to the lithography. Why electron beam lithography has better resolution, or what does the lithographic process? So related to lithography from unit 4. So let's talk one questions related to lithography. First thing is that what do we mean by the lithography? So if you'll see carefully, then lithography is basically used for pattern transfer. Whatever the fabrication you wanted to do on the wafer, so that is the pattern transfer. So what are the types? So definitely indirect types only, that is optical lithography, and then the electron beam lithography, the ion beam lithography, X-ray lithography. These are the examples, right? So what is this optical lithography? Optical lithography is pattern transfer process in which the light source is projected through a photomask. You have to remember, onto a photoresist. So there are the four things you should remember. What are that? UV light, one, mask, two, photoresist, three, on the wafer, four thing, right? So these are the steps wafer you should prepare the photoresist. Because of photoresist only you will do soft backing, that is the the to make it hard you have to you go under this process of baking, that is just giving the temperature so that the solvent parts will evaporate, nothing else. Mask alignment, that is the masking, it is also important for photoresist and development, hard bake, etching and implant. Etching is a part, just removal of unwanted layer. For electron beam lithography, this is also the lithography. Same things. Objective is to transfer the patterns from mask to the wafer. But here you need not require any mask, right? Mask free. Why? Because you are going to use the source, that is not here. There is no UV, no light, no UV light here. Electron beam instead of the UV. Okay, so electron source here it will be, then beam focusing, and the major advantage is that this is more accurate. Rest other things you can check it. Lastly, the questions is for last questions we are going to consider the related to the fabrication, right? So explain the fabrication process. Steps in need diagram for CMOS inverter, and again another question like process in fabrication related to the shingle anvil. So both questions are almost related. That is CMOS inverter. We have already discussed in our previous sessions. You may go through that, but shortly I'm going in to this detail, right? So this is for your inverter circuit fabrication. How can you fabricate? So step one, that is your substrate preparation, and then the step second is your veil formation, Well formation is required for P MOSFET and the N type of MOSFET for both, right? It and the what type of the MOS like well will you form it depends on the type of the MOSFET. For N MOSFET you are going to use P type, and then P MOSFET you are going to use the N type. After that, you have to develop the oxide layer on the top, then the silicon formation, polysilicon gate formation or above to the gate, and then lightly doped drain. You are going to develop the drain and the source by using diffusion technique. Then finally spacer formation, that is have to keep the spacing between that, and then drain and source formation, solidization, then dielectric deposition technique. You are going to deposit the SiO2, and then finally metallization that will provide the contact among the all layers, right? Lastly, whatever the problems you might have, you can go for the annealing process in order to remove the crystal defect inside your fabrication. So that is the final step, right? So these are the steps for fabrication. Here is the final steps. So if I'm revising, this is the substrate, this is the anvil formation, then the drain and source formation, your gate formation, your gate, and then polysilicon metallization. So these are the techniques, right? So thank you for listening. If you have any doubts, please drop your comments. So we'll continue to discuss some more interesting facts about this related course. Primarily, we'll focus on the gate in upcoming sessions. Thank you for listening. If you have any doubts, please drop your comments. Thank you.